What are you giving the evil eyes
It's
to?
not you. It's not you. It's me skeptically wondering if my technology stack is in operation. And of course, the only way to know if it is if someone acknowledges our presence. Do you find that whenever you start streaming on YouTube, it just immediately just says bad? Just says you're always bad. You start out bad. Yeah.
Yeah, it's like it needs to put you in its place to inspire you to do better to get rid of the bad warning.
Yeah. Yeah. I have so much bandwidth. It's not possible that my internet connection is bad.
But it could also be on their end. It might not be you, Fraser. It could be them.
It just starts that way. And so now it's saying
Yeah.
okay, but the okay is red. So it's not the good, it's not the green good, it's just an okay. It's like it's
It's full
fine.
of
I
hate.
know. I know. It tells you, yeah, I think that's exactly it. Like don't feel like you're the strongest link in the chain. We are the weakest link. Google wants to
I
make
hope
sure
that's
that
not
we
true.
always remember that. Oh man. So have you thought about this whole Google Plus thing?
It's sad.
Yeah, it really is. And all that content, and all those conversations and all those relationships, and that is the inevitable and I mean we both I mean you wouldn't be watching this live if it wasn't for what we had started to do on Google Plus and figuring this stuff out and all the
Yeah.
connections and friends that we made. And those are going to
Well,
echo.
and the difference between YouTube Live and Google Hangouts on Air was the community aspect. You could add people to circles, you could share
Mhm.
circles, you could follow this circle or that circle and suddenly gain this richness of humans. And that circle feature is something that just hasn't existed on any other platform. You can't readily share lists on Twitter. Um, there's no way to just suddenly say, "Oh, I found my people," and
Yeah.
step in with all of them the same way that you could on Google Plus.
And it's so weird that they're just going to wipe out all that content. Like that's their power move is to just go,
Well, that's Google. That's Google's nature.
yeah,
They killed off Google Reader. They killed off FeedBurner.
Google Waves.
I Google. Well, Google Wave was kind of the application awaiting a purpose. Uh, but
Still,
I mean, and now Google Inbox is going away March 1, and I'm like so
I
angry.
never used it. So,
It is fabulous, and it has killer features that made it so that I could finally almost keep my inbox under control. And yeah, I'm sad. I has a sad.
oh. So, and this is sort of partly to remind everybody that Google Plus is going to be going away on April 2nd. And if you want to stay a part of the various communities and all of the friends that we made there, you're going to want to go to the Weekly Space Hangout crew. They're working on their own forum. And of course, there's the
Yeah,
CosmoQuest forums as well. So there's some places that you can go that people have been stewarding them for years and years and years. And this stuff will live on.
it's true.
It is true. So go to wshcrew.space. Of course, here we are, feeling sad about a platform going away on YouTube, which is another Google platform. Don't take it away, Google, please. We like
Well,
it.
they bought YouTube. A lot of these other things. Google is one of the companies out there that allows their employers a day a week to be super creative. And so different projects such as Google Earth have arisen out of groups of Googlers coming together and doing, we're going to do this awesome thing.
Yeah.
And some of those awesome things are allowed to live and some of them die. And then sometimes Google just buys shit. And YouTube was a purchase. And I think that it's very different nature and the fact that it earns them so much revenue is really going to allow it to live where so many other things were forced to die.
Yeah. Yeah. No, I don't understand, but I'm sure someone is looking at the math of it. So, okay. if you're wondering what it is that you stumbled into, we're going to do a live episode of Astronomy Cast. We're going to record it. You're going to watch. And then when we're finished, we will stick around and we will answer your questions about space and or astronomy.
My coffee is very hot.
Good. I almost made
Okay.
coffee, but I decided not to. I'll have coffee afterwards. I'm definitely under caffeinated though, so I need to reach caffeine parity. And unfortunately, people watching the show won't get that. Oh, I've got one thing. Actually, I'll shamelessly self promote it in the actual show. So
Okay. Cool.
okay,
Anything else?
I'm ready.
I am ready too. I
pressed
am
record.
pressing record.
I did it.
We are recording.
Okay.
Hello, Susie.
Here we go. Astronomy Cast, episode 517. Fritz Zwicky and the Zwicky Transient Facility. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser, Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, a senior scientist at the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing?
I'm doing great, and I've got like a couple of things I got to quickly log roll here. One is that you and me and Skylius and John Michael Gaudier and Paul Sutter are all going to be leading a fantastic star party in Joshua Tree, California, and that's going to be in the end of June. And if you want to be a part of this, go to astrotours.co. It's called the All-Stars Party. We're going to be setting up a bunch of telescopes. We're going to be teaching you the night sky. We're going to be hanging out. We're going to be going on adventures. It is going to be fun for the whole family. So check that out. The second thing is, did you know that Oceanside Photon Telescope has a new podcast as well? It's called
I
Space
did. You
Junk.
and I have both been on it.
Separately. So it's called Space Junk. And I'm not sure what wonderful topic they picked for you, but for me, they wanted to talk about conspiracy theories. So that was fun, and I couldn't help but turning into a conversation about the Fermi paradox and colonizing Mars. But still, we did talk a bit about the sort of the nature of conspiracy theories. So if you want an interesting podcast to listen to, check it out. Tony Darnell and Dustin Gibson are the hosts, and ran for a long time. It was a very long conversation, and we had a lot of fun. I was well caffeinated during that.
And some of you may already know Tony Darnell. He's done some work with us in the past, and he's the voice behind Deep Astronomy.
Yeah, and Tony Darnell, Dustin Gibson, super fun to talk to, hilarious, and it was a great thing. So check out their podcast, Space Junk. One of the most influential astronomers in the 20th century was Fritz Zwicky. He had his hand in the discovery of dark matter, gravitational lensing, supernovae, neutron stars, and he also worked on a few more controversial ideas like tired light. So let's learn about Zwicky. Pamela, you chose Fritz Zwicky this week. What led you to believe? There's no mission? Why does he get a show?
Well, there's a new telescope facility. So one of the things that I noticed this week is we have a brand new reused telescope. For years and years and years, the Palomar Sky Survey had been repurposed to, instead of doing a sky survey, the Palomar Schmidt telescope had been repurposed to doing the Palomar Transit survey. And they'd been looking night after night at fairly okay, but not great resolutions at the sky, looking for things that flicker, flare, and move in the night. Specifically, their goal was to uncover supernova upon supernova so that we could better measure the Hubble constant and the expansion of the universe. Now, recently, they upgraded the system and gave it a new name. They named it after Fritz Zwicky, which is an individual who's the kind of character who's really worth discussing. And I felt that this upgrade to the system, this new camera they stuck on the telescope, the new discoveries they're making, well, it all added up to one new episode highlighting the guy who came up with the idea of a spherical B word.
A spherical B word?
Well, I'm going to go ahead and say it. A spherical bastard. Fritz Zwicky is perhaps best well known among graduate students as the individual who came up with the concept of an idiot who is an idiot as seen from any direction is a spherical bastard, because spherical, same in all directions.
Yep, an idiot
Yes.
from all directions. All right. So who was Zwicky?
Zwicky was a European scientist who lived in a number of different nations throughout his life, but claimed Switzerland as his home. He moved to the United States after World War I, where he took up residence at Caltech. He there worked with Bada. He was a professor in his own right, and he was a tremendous observer. And along with doing amazing observational astronomy, he thought long and hard about the things that he was doing. And I've seen various sources that claimed that he is the person who coined the term supernova, that his colleague Bada is the person who coined the term supernova. Whichever one it was these two gentlemen working together that figured out that a large star dying violently, exceeding Chandrasekhar's limit on how large a white dwarf can be, would have an explosive event going from star to neutron star. And that explosive event would be a supernova. Having come up with this concept and evolution of a star, Zwicky went out and did the observations to find not just one, but over 100 supernova. This was a record that was not to be displaced until CCDs came online. He actually did all of this work entirely by eye, comparing image upon image.
Oh, that's just amazing. And there's a great quote that I like about Zwicky. I don't know if you ran across this one as well. When researchers talk about neutron stars, dark matter, and gravitational lenses, they all start the same way. Zwicky noticed this problem in the 1930s. Back then, nobody listened.
This is true.
Yeah.
This is true. He was the kind of person who um everyone I've ever talked to who knew him while he was still alive referred to him with strong terms of he was brilliant, but hell no. They just noped him. He was curmudgeon is the word most often used. But he took personal pride in being a mathematician who did all of his work alone. And because he was happy working alone, well, if you're happy working alone and you're doing great research working alone, you don't have to be nice. And Zwicky was not nice. He did good things, but there's a difference between being someone who does good and being someone who is nice. So he's someone who dedicated huge sums of money to reshaping the world after World War II into being what he wanted it to be. He helped collect books to send to World War torn nations to repopulate libraries. He spent vast sums of money to help support orphanages. He created a foundation that continues to this day. He was also not someone you necessarily wanted to have lunch with.
It sounds like Isaac Newton a little bit. So was it just that he was grumpy or angry or insulting? Like what?
The impression that I've always gotten is he was someone who was so brilliant that he just saw how things fit together, but couldn't be bothered to explain things clearly and well to those around him so that they actually wanted to listen and care about what he was saying. So for instance, he used the virial theorem to figure out how galaxies in a cluster should move once everything had settled into place. So the idea is that when galaxies are first falling into a cluster, when everything is still interacting, you'll have one set of velocities, but over time, things will relax and you should see a set of different rotational orbital speeds. And when he looked at galaxy clusters, the Coma cluster in particular, he didn't see the velocities that virial theorems had predicted. And when instead of going from virial theorem to predicted speeds, he went from the speeds he measured using the virial theorem to calculate the mass of these clusters, he found that the clusters had to have a significant amount of mass that he wasn't detecting. He, along with Vera Rubin, who worked completely separately, instead looking at our own galaxy and at the orbital velocities of gas in the outer parts of our galaxy, they both independently determined there had to be this additional matter. With Zwicky, he named it dark matter, but not in English, and that's the name that stuck.
Wow. And
And
when was that? That was like in the what, the 40s, the 30s? Like
yeah, it well, the saying is he thought about it in the 30s,
and,
and
and
that's
nobody
kind of
listened.
what he did. And
Yeah.
nobody listened.
And that, I mean, even that first observation, I mean, this idea that here in the solar system, you see the planets going around the sun, and all the different planets are going different speeds because they're I guess battling the gravity of the sun, and the farther you go, the slower you have to go to be able to balance out that gravity. But imagine if every planet in the solar system was all moving at the same speed, no matter how far away they were from the sun. It would be such a weird thing to uncover, and not at all what you'd be expecting. And that leads to the, like, so there has to be some other mass, something that's going on. And it's like, I wonder, like, as you show people your observational evidence of this, and go, look what's going on. Like, it's different than a solar system. What's this about? And people just kind of going, I don't really want to think about this right now.
Well, and it was more than that. It was just sort of like, Zwicky, come on, how many great discoveries are you gonna have?
There's
Because
too many. We don't have time.
so he went from pointing out dark matter with his studies of the Coma Galaxy Cluster in 33 to using the Palomar-Schmidt telescope in 34 and 35 to do studies of the supernova concept. And I mean, he kept doing that until he'd found over 120 all by himself. And then from there, later on in the 30s, he got to thinking about Einstein's theories and the prediction that Einstein had made that gravity could bend light and create Einstein rings and things like that. And he's like, distant galaxies can do this. So he went looking. And in 79, someone finally found the twin quasar, the galaxy that had been, well, it had its light bent. And so Zwicky said that should happen back in 37. And then he just kept getting in on other people's business. In this case, I mean the business of science. And so while he was studying Coma Cluster in 33, he of course was thinking about galaxies in general and the expansion of the universe in general. And the expansion was something that was getting well discussed as early as the late 20s, so 29. So he started complaining about it in the 20s, but he came up with his own idea of tired light to
Mm-hmm.
basically say this whole expansion of the universe stuff, we don't need that.
So hold on. So
And
let's just go into this for a second here. So the, like, when we think about the, and we've done a whole show on Hubble, and did his research, I think, with the Palomar, with the same telescope, right? But was
he was using Mount Wilson
Mount Wilson,
Observatory.
that's right, yeah, and was observing these Cepheid variables and noticing that the color that was coming from these galaxies and other stars was shifted to the red from what we would see for stars that were relatively close by, and they assumed that this meant that because it was Doppler shifted, it was shifted to the red. It meant that the light wavelengths were stretched out, and so these galaxies were moving away from us. And everywhere you looked, galaxies were moving away from us. And Zwicky proposed that no, it's not that these things are moving away from us, but that the light is losing energy.
Tired.
I know it's getting tired. Oh, that's but like what was the mechanism that he was proposing?
Well, he literally felt that there were mechanisms by which light would lose its energy as it traveled through space. And that this Redding effect was I mean, literally, it was the light getting tired, losing energy, just like we do throughout the day. So here you can imagine, as the light goes along, it's just shedding a little bit of energy here, a little bit of energy there, getting a little redder as it goes, adding its energy to the universe. And while this might have been a great explanation for dark energy, which had not yet been discovered, um, it turns out that what you would observe of our universe if light does get tired versus what we actually observe are not the same thing. And and also the reason that he felt the need to put forward this idea also turned out to be a bad early measurement. So one of the reasons that Zwicky was like, nope, I'm not going to go with that whole expanding universe thing, was originally people thought our universe was expanding at perhaps hundreds of kilometers per second per megaparsec. And that is extraordinarily fast. And while there's no real reason that the universe can't be expanding that quickly, it just was an uncomfortably large number. And Zwicky saw physical reasons why such a large number just didn't seem to make sense. And so in the late 50s, his colleague at Caltech, Bada, who's actually my academic grandpa, um, Bada was able to say, okay, we screwed up. Using Cepheids, we can slow down the expansion of the universe. The universe is actually expanding more like 100 kilometers per second or slower, much better. And that helped Bada. And then the other thing that ultimately, that helped Zwicky, but ultimately the thing that really nailed it down was if you have what's called a steady state universe, a universe that has the same amount of stuff over time, and it's just either new matter is coming in or the light is getting tired as it travels, you would expect that the structure we see today would match the structure we see in formations that gave their light off at great distances.
Right.
And as we look at light from more and more distant objects, we don't see the same kinds of structures. We don't see the large, well-defined, large-scale structure of today echoed in what we see in the past. And this difference in, well, this fundamental difference in the structure of the universe over time means that it's not just tired light, it's the universe expanding and the structures changing with that expansion.
And of course, I mean, one of the most important observations ever made is the cosmic microwave background, and that like is this afterglow of the Big Bang. And for you to see that and know that that is the moment when the universe had cooled down to the point that it could release light, and you can calculate what that temperature was when radiation could finally be released, then that just tells you, right? Like, there you go. Now you know that that's because that is far away and moving quickly away from us, not because the light was tired and there's a weird place that happens to be 13.8 billion years in all directions where this interesting wavelength of radiation was released. Like, it's a right? Like once you, but this was before, we're probably 20 years early from the discovery of the CMB.
Right.
And so,
and this was,
I'm sure
again,
he
going
recanted
back
later,
to that,
right? I'm sure.
well, he did more or less, but usually grumblingly. He died in the late 70s. So it's hard to imagine just what he might have thought had he lived long enough to see dark energy come into existence, to see a day where we understood that that dark matter that he was one of the first to spot was broadly acknowledged. We now know our universe is accelerating, and there's some evidence that the acceleration itself is accelerating. It's not the universe that Zwicky was trying to figure out how to understand. And steady state doesn't stand up to modern observations.
Right.
And tired light really doesn't stand up.
Right. And actually, there's a conversation in the chat right now about why I mean, the steady state universe is the one that we preferentially go towards, we gravitate towards, pardon the pun, because to have this thought that the universe had a moment that it began and that it has a future that it will end are troubling ideas, whether it's a big crunch, whether it's a big rip, whether it's a heat death, they're all just like there's no way to stop the inevitable end of the universe, and also the fact that the universe started in a fairly, I mean, obviously beyond our concept of time, but to 13.8 billion years is an amount of time that, say, the Earth has, has experienced a significant fraction of that. And so just to think, like, where did it come from? Why did it happen? Why is it expanding? What led to that expand? Like, they're all really troubling ideas. And
I don't
as we
think they're troubling, but they definitely changed the mainstay philosophical ideas of the time. When Einstein was working in the early 1900s, philosophically the concept was, well, the universe is as it's always been and it shall always be. And this was in some ways driven also by religion, even though that makes no sense considering the dominant religions of the time and even the dominant religions of today all posit a universe that has a beginning, a middle, and an end. Um, it's just scientists being human beings. We sometimes get biased, and I think the troubling part is that human beings have this bias. The fact that we as human beings, with our bias, with our broken minds, can figure out the universe is 13.8 billion years old, plus or minus a snort, and that it has a beginning, and that it will probably, well, the inevitable heat death of the universe seems to be inevitable. I think that that's not troubling, but actually kind of awesome.
um
Sorry,
no no no
soapbox,
yeah
stepping
no no
down.
no no I I find all because I want to live forever in a succession of robot bodies, and to think that in fact, no matter how strong and tough I make my robot body, it's either going to get smushed together, torn apart at an atomic level, or just cool down to the background temperature of the universe. Those are all troubling for my desire to live forever. But
And I, for one, do not want to live forever. And my retirement account is a very good explanation of this desire.
retirement account empty. That's it. That's the end of life. Now, what else did Zwicky do?
Is that not enough?
Yeah, well, so there's some stuff that I think was really great. Like, you can see some of the papers that he wrote. So he did one in 1934 called "On Supernovae," and he did a bunch of consecutive articles, and in that he introduced the idea of a supernova and a neutron star, while Oppenheimer did his paper on neutron stars, I think in the 50s. So it's just like, again,
Yes.
just 20 years early from everybody, and he just wasn't able to make it stick. Now, in addition to the work that he did in science, but he also did a bunch of other things. He was involved in, um, you know, uh, was involved,
Crystallography.
and it was also involved in parts of the war and rocketry and things like that. You know,
And he was an engineer. He has a whole number of different patents, including patenting the first jet engine that worked underwater. So this is someone who started with math, spoke multiple languages, landed at Caltech as a professor. Uh, he did all the things basically.
one of the things that's funny is he's one of the people who originally didn't think that a rocket would work because there was no atmosphere for the rocket to push against. You couldn't get this equal and opposite reaction, and then later admitted that he was completely wrong about that because obviously,
Which is how you should do it if you're a good
yes, yes, of
scientist.
course, you take a position, the evidence shows you that you're wrong, and you apologize and accept this new evidence as
I
the
don't think he apologized.
I didn't apologize. All right, so let's talk a bit about the Zwicky Transient facility then, and just sort of what its job is and what it's going to help us discover about the universe.
So ZTF, as it is affectionately called by people who don't want to type out all of the letters, is a new facility built onto the Schmidt telescope, the Palomar Schmidt Observatory, and this particular facility is a replacement to the Palomar Transient Factory and is making it possible to observe 3,750 square degrees of the sky per hour down to 20.5 magnitude.
Wow.
Now, this is a 48-inch telescope, so it's about 4 feet across. That's a little over a meter for those of you thinking in metric. And this is just huge.
Yeah.
Let's just go with it's just huge. And the goal of being able to do this is they want to find supernova just as they go off. So by observing as much of the sky as possible on any given night where the sun has a nasty habit of rising and the planet isn't always pointed where you want it to be, by observing as much of the sky as the night allows each and every night, this telescope is catching supernova shortly after they explode, allowing astronomers to follow through the entire light curve. This is particularly important in two different scenarios. The first is we're still trying to understand if all type 1a supernova, the kinds of supernova that are created when white dwarf stars eat too much material off of a neighbor star and explode, we're still trying to verify that all of these things, when they explode in the exact same way, meaning that we can successfully use them as standard candles to measure the expansion of the universe. The other thing is we're still trying to understand the nitty-gritty details of all the different ways that large stars find to self-destruct. We're trying to understand what are the nuances that come with metallicity, the nuances that come with size and environment. And by studying the evolution of each of these different exploding systems as they take place, we can understand what is the ratio at which different materials, by which I mean different kinds of atoms, are produced in different stellar deaths. We learned just within the last year that gold, well, more often than less often, comes from two neutron stars colliding rather than from just supernova. We are now also slowly starting to learn what kinds of supernova produce all the other stuff. By combining this information with our understanding of what's called the initial mass function of stars, that function that describes this is how many big stars you get, this is how many medium stars you get, we can start to build up an understanding of how different kinds of atoms came to populate our universe, being able to say, well, this number of generations of stars, you had this stuff available to make planets. This number of generations, you had this amount of stuff to make planets. We're basically trying to figure out what ingredients were available to make that recipe that produces worlds like our own.
And so this is the greatest supernova hunter ever developed until the
And
Large
along a
Synoptic
way,
Survey comes online, of course, which I can't
of
wait.
course.
But I mean, just to be able to observe the entire, like it's going to observe the entire path of, the entire plane of the Milky Way every night. It's going to be able to, as you say, it's going to be able to observe the entire night sky every couple of nights. It's going to be able to gather just enormous amounts of information. And when you think about like the brightness of things like, I'm trying to remember what the magnitude of Pluto is, but it's in the teens. So to be
Yeah.
able to get a 20th magnitude object is that's pretty dim. So
And
that's fast. That's good.
and and you can get down to 20th magnitude in about 10 minutes in one color with kind of a telescope. You can do it faster with higher sensitivity, with bigger pixels. But it's not just doing one field in 10 minutes, it's doing field after field after field in 60 minutes, getting a huge area across the sky. And since it had its first light back in November, so this telescope's only been operational for a few months. It's a baby facility. The telescope itself has been around. This camera on the telescope is only a few months old. It has already found an asteroid of a kind we had previously never found before. It found an asteroid that's like determined to live within the confines of Venus's orbit. It goes above the plane of the galaxy, the plane of the milk, the plane. It goes above the plane of the solar system. It dips below the plane of the solar system, but its distance from the sun is consistently smaller than Venus's orbit. And that's not anywhere we ever expected to be finding an asteroid.
Right.
And it's going to help us know what we don't know. And then LSST will, of course, even fill in more pieces.
Yeah, and that news was announced like today. So
2 days ago.
again, we get to see all the benefits of Pamela being up to date on all the space news. All right, Pamela. Thanks for the show. Thanks, Fritz Zwicky, and the people working on the ZTF. We'll see you all next week.
Bye bye. And now we save. So yeah, Zwicky and Bada work together at Caltech, and my dissertation advisor, John Cormandy, was Bada's graduate student. And Cormandy had stories that he was not someone who ever spoke badly of anyone. John Cormandy is just inherently a very nice human being. But the body language was that of, well, it's the same body language I think I get at the thought of having a conversation with Virginia Trimble. She scares me. I'm pretty sure that even if I just asked her if she wanted coffee, I'd somehow come out of that conversation feeling somewhat scathed. And yeah, he, yeah, Zwicky left people feeling scathed.
This is really cool. I'm pretty interested in this. I love the idea of transient astronomy, and I kind of want to do an episode on this now because it's. I don't think it clearly hasn't gotten enough love out there. So I think I'll consider doing an episode on, especially with this new discovery that came out of this new asteroid. So
This is 517.
517, yeah.
Okay.
All right, hit us up with your questions. Arjone asks, would a planetary nebula be done forming planets before it got away from its stellar nursery? I'm thinking that nearby supernova could sprinkle necessary elements on the forming planets.
So go ahead.
Oh, yeah. So just do the elements for planets. Can they rain down from supernova after the fact, or are they sort of there piled up, before the planetary formation starts?
Well, you can definitely augment things. And the way to think about it is we know our own world was augmented from stuff coming at us just from within our own solar system. Our planet would have initially been largely baked dry by the young, hot, early, angry sun. And then later, ice chunks from the outer solar system, by which it now looks, meteors that had large water components rained down from the middle of the solar system on our heads and brought us the moisture that allows us to exist. The water in your body once was inside of a meteor, and that's kind of cool. Now, at the same time, there's nothing to say that early planetary disk, while it was in the process of forming, got rained upon by additional material, but not with so much force that it disrupted the disk. That's the real thing you have to worry about, is if a supernova goes off too nearby, that solar system might get blasted apart before it even finishes figuring out what it wants to be when it grows up. But yeah, you could augment systems. Another way our planet was augmented when the Chicxulub crater was formed, the impact that killed the dinosaurs. We ended up with a layer of iridium across our entire planet that came to us from that meteor. Now imagine instead that you have chunks of material that got blasted together in the supernova explosion. It's possible that those chunks of material can rain down as well.
Bill Sugden is asking, how are the grant requests going?
That would require the grant to have a deadline that the government has set. And unfortunately, pretty much everything right now with our government is TBD. Mm-hmm. I'm waiting to see if our government shuts down next Friday before I start getting on the phone to people, because if the government shuts down next Friday,
yeah. A lot of scientists that I've talked to are still dealing with the repercussions of the government shutdown, that it's going to be a while. And so,
but here is my answer to all of those problems. Come here.
Some kind of dog-based answer? Oh, puppy.
Yes. Whoa, headphones. So it turns out when you're having a very bad day thinking about your grant funding, the solution is to be hugged by a puppy.
Aw.
So, yeah. All I have to do is offer you a blue-eyed puppy in exchange for all the sadness brought about by the government shutdown.
But if anybody knows of any either grants or puppies, let Pamela know.
I need grants more than
Yeah,
puppies. I have a puppy.
you've got all the
I
puppies
need
you require.
grants.
Um, George Edgerog asks, "What's the earliest that an Earth-like planet could have formed in the age of the universe?"
We're still not sure. I mean, if you had the exact right place, it probably could have formed a few billion years out. So we formed roughly 8 billion years, and we're probably not the oldest planetary system out there. Um, yeah, this is one of the things we're still trying to figure out, but conceivably a few billion years after the Big Bang.
So what would be the bare minimums that you would need? Like you would need some heavier elements. You would have needed some generations of stars first.
You'd need a few generations of stars, but more to the point, you'd need a few generations tightly bound together so that you could have the open cluster that our sun formed as part of, to have metals, heavy elements permeating um, the entire star forming region.
Right.
So have the supernova go off, have time for the material to become very well mixed, have that well mixed material form a large nebula, have that nebula form stars, and then form our star, our planet, drift apart, and then you have our solar system.
So, but definitely a couple of billion years after. I mean, the interesting thing that astronomers are seeing now is they're seeing surprisingly well-formed galaxies early on in the age of the universe, large spiral galaxies that are just a couple of billion years after the Big Bang. So you would expect that in a galaxy like that, you could have planets like the Earth around sun-like stars. So, one of those ideas that, like, when you think about the Fermi paradox, the reality is it looks like the conditions for life in the universe have been around right to the very beginning of the for as far back as we can observe. So where is
Yeah.
everybody? Right.
Well, and that's where it comes down to how well mixed was the material, because getting stars and structures early on, we can actually explain with turbulent inflow. It's the getting the supernova material to mix in the right ways and places that we don't know how quickly that occurred yet.
Right. Someone is noting, John Seinfeld is noting that the UK Mars rover is going to be called the Rosalind Franklin rover after the DNA pioneer. How
Yes,
cool is
yes.
that?
We actually discussed this today over on the Daily Space. And one thing that I just want to point out to everyone is there's going to be this desire to shorten Rosalind Franklin, not to the Franklin rover, but to Rosie the rover.
Mm-hmm.
Don't do that.
No. How about Rosa the rover? Rosalind?
Rosalind.
Rosalind?
Or better yet, call it Franklin, the
Roverlind?
same way we called Cassini. We have this habit of calling spacecraft after the last name of the human. So it's the Hubble Space Telescope,
Right.
Herschel, Cassini.
So the Franklin rover.
And yeah,
Okay.
and Rosalind Franklin, it was in a book disparaging her work and her contributions that Watson referred to her as Rosie. So don't use the name that was used to disparage her, to celebrate her life. And this is a woman whose work led to 3 different men getting 2 different sets of Nobel Prizes. She died quite young at 37 of ovarian cancer. And her early work on DNA led to Watson and Crick getting a Nobel Prize. And then one of the men who was in her research team after she passed away went on to continue her research and then get the chemistry Nobel Prize. She was a tremendous researcher who died far too young and with far too little credit for what she accomplished.
Danger Zone is noting Rover McRoverface is, always a possibility.
Franklin
Rover. All right. Good luck. Good luck for it not turning into Rosie the Rover. Just good luck with that.
Well, it's going to take all of us working together.
Okay.
So all of us together can do this.
All right.
We can do this.
All right. I'll throw my energy at it. And Danger Zone asks a question about dark energy and expansion. Is the universe expanding faster in the middle of voids and slower near the filaments, or is it uniform across space?
Um, okay, so there's a difference between asking about the universe's expansion rate and the typical rate of motion of things in different places. So, as far as we know, the space-time continuum is at any given moment in time expanding uniformly across the volume of space. How fast it's expanding does vary with time. Now, when we look at how things are moving in various places, the gravitational pull of the surrounding material affects that. We, for instance, can measure our motion not just relative to how we're being carried by the expansion of the universe, but we also see our motion toward the Andromeda galaxy, which we're gravitationally getting pulled toward. We can see our local groups falling into a nearby supercluster. All of these different motions take place. And when we look at material that's inside of voids, the material insides of voids is getting pulled out towards the nearest walls and superclusters. And so that motion is on top of the
Right.
expansion of the universe and is driven not by the expansion, but rather is being driven by gravitational force.
Right. So if there was no material in the universe, then the expansion of just space itself is equal. Every cubic meter of space is moving away from every other cubic meter of space at roughly the same accelerating rate. But with the matter inside the universe, it is getting pushed and pulled by its own gravity to change slightly how that expansion is happening at various local levels. And so there's just as
Yeah.
much dark energy between us and Andromeda as there is a place between two spots that have no galaxies. It's just that the gravity between us and Andromeda is greater, and so it's pulling us towards each other.
Yeah.
Um, John Suffield asks, how small and insignificant is our sun? How many light years will you have to go until you can't see it with the naked eye?
Um, it's not really small and insignificant. It's not like it's a red dwarf star.
Yeah.
Once you get out as far as Pluto, it starts looking more like Jupiter does to us than like how we imagine a star looking, but or how we imagine a sun looking, but it's still sufficient to create a twilight day. I I mean, if you get as far as Alpha Centauri, it's going to be visible with binoculars and be very starlight. So basically, if you go to the nearest star, it I mean, it is a star, so saying it looks starlight is dumb. Apologies for
Right, right.
stating
But
the
Alpha
obvious.
Centauri is,
Um,
the Alpha Centauri stars are roughly the same. They're a little smaller than the sun,
yeah,
and Alpha Centauri is one of the brighter stars in the sky, and that's 4.5 light years away. So if you were 4.5, if you were on Alpha Centauri, the sun would be one of the brighter stars in your sky. But if you go 10 light years away, 20 light years away, 30 light years away, it starts to become a pretty dim star that you can't see.
yeah, and so within our solar system, you can see it is a disk, like we can see Jupiter as a disk, but it becomes point like even with binoculars at the distance of Alpha Centauri.
And the thing that's amazing is that when you look up into the sky and you see all the stars that you see are actually incredibly bright, hot stars. You're seeing red giants and blue, large stars, and there actually aren't a lot of stars that are small and dimmer because there aren't a lot of
Yeah,
stars nearby us. And it's just that you're seeing things that are 300 light years away that just happen to be
yeah,
enormous stars. So we are not seeing the universe as it really is. We're seeing like the highlight reel of the Milky Way. Um, Astro YYZ asks, is there a Zwicky catalog for observational observers with backyard telescopes like a Messier or an NGC list? Is there a Zwicky catalog?
I think there's a Zwicky catalog of irregular galaxies. Let me double check that
Yes.
it's him and not someone else.
How many Zwicky
Galaxy.
astronomers are there? But yes.
There's only okay, so it is the Zwicky irregular galaxy catalog. Um, so that is a stunningly beautiful catalog. It was made using glass plates. It is worth visiting a historic collection at a university just to flip through its pages. Uh, some of them are backyard friendly. It all depends on how big your field of view is. In some cases, you need a big view and you can't see the little things. In some cases, you have the little view and you can't see the big things. It's the kind of catalog where you really need to have multiple kinds of telescopes to see all the different kinds of objects in the catalog. But it's stunningly beautiful.
Michael Meyer is asking, does the total amount of matter in the universe offset the effect of dark matter?
Nope, because when we talk about how much dark energy, dark matter, and
He was
regular
saying dark matter.
baryonic
Yeah,
matter,
yeah.
there's what we're talking about is the percentage in any given volume. So uh, the density of dark matter is constant with volume if you look at a large enough volume. Sure, it clumps up here and there, but so does luminous matter. Everything clumps up here and there. But when you look at a large enough volume, that clumpiness goes away. And so we start talking about what is the percentage of each, and dark matter consistently dominates over luminous matter, and then dark energy dominates over both of those.
Oh, and he was saying dark energy. So does the total amount of matter in the universe offset the effect of dark energy? No.
Nope, same issue. Now, at the very early days of the universe, when the universe was much smaller, because the amount of dark energy varies as a function of time because it is almost constant with volume. So when the universe was a smaller volume, it was matter dominated. Now that it's a larger volume, it is energy dominated. Just mess with our heads. So early on in the universe, matter played a larger role.
And now, this fairly tentative observation that was made of quasars says that maybe, in fact, dark energy, the strength of dark energy, can change as well over time.
Right.
So it's not
And
constant; it
and
could be variable.
it's unclear if that means that the force itself is varying, if the volume, if the amount of dark energy per cubic meter is varying. We have no clue what dark energy is. So yeah, it's just fascinating.
Yeah,
All we can say is dark energy appears to change with time. Very tiny amount. Very, very, very
very
tiny
tiny
amount.
amount, but the puts the big rip back on the table.
Yes.
Olaf Lindquist asks, if time dilation accelerates as you approach a black hole, does that mean that when you pass the event horizon, you will have passed to the end of time, seen from the outside?
Yes, yes, it does.
Weird.
So
So,
when you watch someone fall into a black hole, you don't actually have to watch them die
right, they'll never die. You watch them
from your
from your
perspective.
perspective, and from their perspective, they watch the universe die. So weird.
Time is wibbly wobbly.
Yeah, exactly. Um, Rich Wilson asks, with the recent talk of the Theia impact helping Earth get its volatiles, is that because they think that Theia had more volatiles, or that it released the volatiles trapped deep in the Earth? Did you see this
Uh,
research?
I didn't see this. This is an idea though that gets recycled periodically, along with the idea that the water was actually just stored deep in the crust of the Earth. Um, I'm going to go with option C. There are lots of different theories. None of them are final at this point, and the truth is probably a combination of different things. Um,
Yeah,
stay tuned.
yeah. I mean, you've got comets, you've got it just forming in place, pulling the water right out of the orbits that it was pulling, and now this idea of the Theia impact digging up and mixing Earth again to get more water out, which is a
Well,
great idea.
Thea definitely did remix the planet
Yeah,
Earth.
yeah.
We had we had a smaller original constituency, and then this Mars-sized object named Thea hit us. The lightweight material splashed up, formed into the moon, possibly in a two-step process, and the heavy stuff was left behind to make our planet. Now the question is, where was the water? Was it in Thea, in the Earth? Was it brought in later? That's where I'm going to ask you to all stay tuned.
Yeah. The answer is coming. They're figuring it out. Let's see if there's any more questions here. Dustin King is asking, how far do you have to go before you start to see the effects of dark matter on rotation curves? I'm guessing our Oort cloud is too small.
Yes, it is. You can do it with a 1 meter radio dish by looking at the outskirts of our galaxy, but you definitely need to look at the outskirts of the disk of the Milky Way to see it.
I mean, there could very well be particles of dark matter right here in the solar system.
Oh, yeah, there are. It's just not a big enough effect.
Yeah.
Otherwise, building dark matter detectors would be a pointless exercise.
So Olaf Lindquist is just adding to the comment about the black hole. So black hole is a tunnel to the outside of the universe, a tunnel made of time, a tunnel that you can never go out of. You get to watch.
Well, the idea of a tunnel to the other side of the universe implies spatial. It is definitely a tunnel to the future. I'll give you that. But do you really want to go there from here, especially if you're going to die?
But I guess isn't your way out when the black hole finally evaporates? I mean, obviously you've been turned into a black hole.
If you want to be a cloud of energy.
Yeah, you've been turned into black hole, and then you are going to evaporate. The parts of you that were added to the black hole will evaporate hundreds of quadrillions of years into the future, and then, so yeah, you made it. You did it. You moved ahead in time, a dramatic period, as a cloud of particles expanding into the universe.
I'd rather be worm food.
Yeah, so that's the problem. And we don't even know like what the conditions are inside the black hole. Like, practically speaking, the tidal forces are ludicrous, that there is possibly this idea, like as soon as you cross in, it's just all hot radiation. So
physics breaks.
Yeah, it would be an awful. Well, physics is fine. We just our
understanding of physics breaks.
Yeah, exactly. All right, we've reached the end of our hour. Thanks everyone for joining us. That was a lot of fun. Thanks, Pamela. Anything interesting happening that people should be aware of?
No, I think I just want to remind everyone one more time that you have the ability to join the two of us, I don't know if I'm pointing in the correct direction, at Joshua Tree National Park in June for the All-Stars Star Party.
Yeah.
And I really recommend this because Joshua Trees is one of the ecosystems that isn't going to last much longer given climate change. So those trees that were cut down during the last government shutdown, those aren't ever going to regrow.
Yeah.
So go experience this amazing landscape while you can. And if you can't make it in June, I'm doing a star party trip through the American Southwest in August. Check it all out, astrotours.us.
.co. Astrotours.co.
Yes, astrotours.co.
Yeah.
Listen to him, not me.
And all the other stuff that's coming up. So lots of fun trips planned. All right. Thanks, everybody. We will see you all next week.